So let's prove the conservation of linear momentum using Newton's second law. So basically, if I'm looking at all of this particle, no one else is interacting with them. But yeah, they are interacting with each other, pushing, hitting each other, pushing each other. If that is the scenario, see what happens, right? As in when a pawn hits another pawn and so on and so forth. So one loses that motion, other gains, right? That you are seen with billets, with carom board, or with hockey. Not exactly hockey, actually. What else? I think those are the most easiest to imagine and get a feel of as of now. And you have experienced it as well, most of you. So this is what we are trying to prove, that the product of any point of time, the product and then the sum will remain the same. That's what we are trying to prove. For that, we'll consider isolated system like this. This is isolated. No one else is interacting with it. Of n particles. So we have around 5, 6, 7 over there. So there are n such particles. And each one can have their own mass. Here, all of them have the same mass. That's what it looks like. But we can have different masses. And they can have different velocities. Here, we can see that particles have different velocities. So that being the case, then the total linear moment of the system. Okay, this is how it will start off. So first is we are looking at total momentum of the system initially, right? So initially, the system's momentum so P is equal to, you guys write the full form and all of that. So we have mass times of, we are adding vector form M2 V2, or in this case U, sorry, initial na, plus so on and so forth, plus M3 U, sorry, Mn Un. Okay, so basically this is your P1 plus P2, all these are initial by the way, comma initial, plus P capital N, comma initial. Now, next thing is we have to talk about, as per Newton's second law, the total force on the system is equal to mass into acceleration. Or yeah, sorry, one more way is rate of change of momentum with respect to time. But as per the idea, there is no external force. Therefore, your forces will be equal to 0. And this implies dP by dt should be equal to 0. And this or dP should be equal to 0. That is change in, this is nothing but, yes, change in momentum should be equal to 0. You're telling that. So from this we can infer that momentum is conserved. Agree? Okay, so one last statement if you guys want to write this. So this entire thing will be equal to momentum of 1, not exactly final, maybe after some point of time, I'll just write F plus and F and so on and so forth. Okay, that's it. It's that simple. You need to copy this and then yeah, this.